it was it was trying to record just a little piece of the screen, so that wasn't good. All right, well, thank you for coming here today. So today we are going to have kind of a special lesson. We are going to go back to the astronomy unit, okay? And something really exciting happened last week, actually, and it was that here the Dawn spacecraft entered the orbit of the asteroid Ceres, okay, the protoplanet Ceres. All right, and so we are going to talk about that and review some of the things that we know about Dawn, about this probe, the mission, how the scientists frame the mission, and the things that they actually decided to do, the instruments they took, and everything. Oh, Haley, thank you. Yes. Well, there are some cheaper houses there, so I think that you don't give up on that. It's a beautiful place, Saratoga Springs, really. So let me go. Here we have this is one of the submissions, okay, for the lesson 17. I haven't given up on this. So in lesson 17, we have a submission that Natasha did as part of her team. She kind of was later doing the team submission, so she submitted her own. But her mission was to send a rover to the moon, okay? So kind of the lunar rover. This is the lunar rover of the Apollo mission. Of course, it is designed to be to be manned, okay? Emma, yes, we are probably not learning about igneous rocks today. Is that okay? I was prepared to teach about igneous rocks too, but I actually thought, this is actually a very, very important event actually that happened, that Dawn entered into the orbit of Ceres, and some really cool things that we want to do. Okay. Don't worry, you'll have your igneous rocks feel pretty soon, okay? You'll be fine, you'll be fine. All right, so here we have the submission here to send a rover to the moon. The question that I have is if it's going to be a manned rover, like this one, the lunar rover, you also need really to send a whole, manned mission, okay? So if it's an unmanned lunar rover, then it would be kind of different, all right? So let's see here. It says that the rover mission to the moon has three main goals. Okay, first, I want to gather as much helium-3 as possible because it can help to power European Union and United States for a year. Okay, helium-3, all right? So I don't know, is there helium in the moon? Okay, how is it going to be gathered? Okay. And then secondly, I want to bring back samples of lunar water. Is there water in the moon? Okay. As far as I know, that they didn't detect any water in the moon. So third, I would like to bring back samples of lunar dirt to check the different minerals present. So we are going to see here, so this is a good mission. Okay. I don't know. Oh, let's see, you may have, okay, I hope that the sound is still okay here. I got a message that it was kind of off for a while, okay. So, is this meeting working better for you guys? So the questions that I have is, okay, is there helium-3 in the moon? Is there enough? So no. What was the question that I asked? Was there if the audio was okay or if there were no problems? Okay. If you can give me some feedback, that would be great. Okay. So I don't know if there's enough helium-3 to be gathered, and then the question would be, okay, how do we gather and how do we send it back? Haley says that we still have problems. I'm going to give feedback here to GoToMeeting and see what is going on here, because I have a very fast connection. Okay. I'm so sorry about that. So the third mission here for this project is to check for different minerals present. All right. So the mission here is to bring back samples of lunar soil to check for different minerals. And we are going to look at how how the probe Dawn can check for the different minerals. Can check for different minerals without actually having to set land on the asteroid or send samples back. Okay, so I feel so bad about this technology. It's really interesting. We can send probes all the way to Ceres and Mars and everything, and we cannot get a good internet connection just here around this world. All right. So one of the problems that I've had with some of the submissions, okay, for this project is that I believe you are still thinking of sending something really big, okay? A lunar rover like this one here, it's huge, okay? There was another one that was thinking of sending a whole probe, about, I don't know, what was it, like 20 feet long or something like that. So Dawn, let's see how big it is. All right, so it says that this is the mass of Dawn when it's wet, meaning that it has all the propulsion, all the xenon that uses for the propulsion. So it's 2,730 pounds. Okay, so kind of heavy. All right. Let's see the dimensions of Dawn. Okay, let's see if we go further down. So it says that Dawn is 7.7 feet long, okay, meaning tall, all right? So it's taller than a person, you can see that, okay? Here is a person and it's taller than a person. And with the solar array extended is 65 feet long. All right, so that is the extent of the solar array when it's all extended. Yeah. So so this is kind of heavy. All right, a couple of 2,700 pounds of weight. What did it take to be able to send 2,730 pounds in orbit? Okay, so let's see what it took to do that. It takes a Delta II rocket. Okay, so it needed a Delta II rocket in order to launch that. All right, so a Delta II rocket is 127 feet tall and 8 feet wide. All right, the rocket itself, when it's full of propellant and everything, is 511,000 pounds. Okay, so about 250 pounds times larger, 250,000 times larger than 250 times larger than the probe itself. Okay, and it cost just a bargain $51 million. All right, so Nah. So that is what it takes to actually be able to launch Dawn into space. That is why when I was giving you the assignment, when I was telling you about, think about the assignment, I was thinking, send a small probe, okay? Just a little thing, all right? Okay, you can still have solar panels that would extend afterwards, all right? But wouldn't it be, cheaper, to launch something smaller? Okay, laptop size maybe. All right, laptop size. Okay, good. I like that. Okay, you can still put a ton of things on that. All right. Sometimes less is more. Sabrina says that. I agree with that. So let's see in these 2,700 pounds of probe, what did they put in Dawn? Okay, what were the components really there in Dawn? So let me see if I have, so the propulsion system, we talk about the xenon ion thrusters, okay, the xenon propulsion system. Also, it has 12 very, very small, okay, let's see, let me close that one. 12 very small hydrazine thrusters for attitude control. All right, so the hydrazine thrusters are really small, and they are just for controlling the small movements of the probe. Okay, so 0.9 N, this is 0.9 newtons. Okay, so a newton is a measure of force, all right? And so here it basically, each of these thrusters has a very, very small force, okay? It doesn't do a whole lot, all right? But the interesting thing is that it applies that thrust for a long time. The ion thrusters, okay, have a force, the ion thrusters has a force of 90 micronewtons. 90 micronewtons. Okay? So a micronewton is a 1,000 part of a newton. Okay? So you see that the ion thrusters have very, very small force. Let's look at one video that talks about this and see how it goes. Okay, let's see this video. This is a very interesting video, kind of doing an overview of the different parts of Dawn, of the probe, and everything.
Dawn is what I call it's sort of the little engine that could. The spacecraft was launched in 2007, and for 14 months in 2011 and 2012, it explored.
So see the size there of the Delta II rocket, okay? So that is what it takes to send those 2,700 pounds up into space. Lots of power there.
Vesta, the second most massive asteroid in the main asteroid belt between Mars and Jupiter. And now it's on its way to become the first spacecraft to visit a dwarf planet, Ceres, in 2015. This is the first spacecraft ever to orbit an object in the main asteroid belt. And it's the first spacecraft in more than 56 years of space exploration to plan to orbit any two solar system destinations. And a mission like this would be completely impossible without ion propulsion.
Ion propulsion uses electricity to propel the spacecraft. We take xenon gas, ionize it, and accelerate it out the back of the spacecraft. The thrust you get out of the ion propulsion system is about as much as a piece of paper pushing down on your hand. For instance...
Okay, did you hear that? So the ion propulsion system, okay, let me bring the camera here. The ion propulsion system has about the same amount of thrust as a piece of paper puts on your hand. Okay, that is 90 micronewtons. Okay, so I really can barely feel the paper, but what they do is that they apply that very small force, because this is all just the force that these ions of xenon, okay, provide as they are accelerated through the thruster. All right, very, very small force. Okay, let's continue with the video.
So the analogy is a car goes from 0 to 60 in about 4 seconds. We go from 0 to 60 in about 4 days. But we keep our foot on the accelerator and we keep thrusting for days and weeks and months and achieve much higher velocities than a traditional rocket.
So did you see that? If a car goes from 0 to 60 in 4 seconds, my car probably goes from 0 to 60 in about 12 seconds. I have an old beater car. Okay, but the probe here goes from 0 to 60 in 4 days, because it's very, very slow acceleration, but they have a long time to travel. So you don't need to go accelerate that fast. You just accelerate for a long time. Okay, so it took 14 months to go to the next part of the trip here. Let's see.
Well, Vesta had been observed by astronomers for more than 2 centuries, but most of that time it was little more than a fuzzy blob of light amidst the stars. So it beckoned, but its invitation wasn't answered until dawn arrived in 2011. And then it revealed this whole fascinating, complex alien world with...
Did you see that, how the probe, as it was going around Vestas, it was actually scanning the planet? We are going to talk about that in a little bit, all right, related to that issue about how do you know what are the materials, the minerals of a body without touching it.
Precipitous cliffs and towering mountains, vast craters punched into the crust, a whole fascinating world that really is more closely related to the terrestrial planets than it is to what people think of normally as asteroids. One of the things that I think is so interesting about Dawn is the way it got into orbit around Vesta. With its gentle, whisper-like thrust, the spacecraft just crept up to Vesta and let Vesta's gravity gently take hold, and the spacecraft then was in orbit. And it spent 14 months there, taking advantage of its ion propulsion system to maneuver extensively to optimize its scientific investigations. And then it gradually spiraled higher and higher and higher until it just gently, elegantly departed and then was on its way to Ceres. Entirely unlike the way conventional missions do it.
Okay, so did you see that? So Vesta is an asteroid, or what they call a protoplanet. Okay, so it's one of the largest asteroids in the asteroid belt. It's the only one that we can see with the naked eye. So it would look like a little star, okay, in the asteroid belt. You need to know where to look at it, okay. But that is this planet, asteroid, protoplanet, mini planet Vesta. It's one of the rocky planets in the asteroid belt. One of the rocky asteroids there in the belt. They must really take the same very seriously. Out of very small things come great things. Yeah, that is absolutely right. Okay. Let's keep looking a little bit more on the video.
All future manned missions to Mars or places like that will take advantage of the fact that this little putt is much more efficient in terms of moving mass from one place to another than the rockets with all their dynamic explosions.
Any mission that requires extensive maneuvering in space really is a candidate for being done with ion propulsion. It really provides a tremendous capability. In fact, even now in early 2014, Dawn has changed its velocity by nearly 21,000 miles per hour. And this has all been done just by this one spacecraft with its own propulsion system. So it's really remarkably capable.
We've got a fantastic team, both at the Jet Propulsion Lab at UCLA and partners around the country and around the world that are working on this mission. A lot of time and effort and years and tears have gone into this mission to make it the success.
See this?
For the future.
See this? It says remove before flight. Okay. Can you imagine if someone forgets to remove the cover of the ion propulsion system before the flight? Okay. Anyone has a comment? Mm-hmm. Okay. So you see here how they are preparing everything for the flight. All right, and yeah, remove the cover before you send it to space.
Sure, I think this opens up really many possibilities for exploring the solar system that would not otherwise be available. And as for what lies ahead, I think Ceres is going to be every bit as fascinating as Vesta is. And I think it's really going to be exciting to see what discoveries Dawn can make there.
Okay, so that was that video showing, kind of how it works and everything. Let's see a little bit of the specifications of Dawn. Okay, there's a couple of places where we can look at this. This is an schematic that is in Wikipedia showing the different components of the probe. And underneath here, it has the legend of what each one of these mean. Okay, so let's try to take a look at each one of these. The dish here is called the high gain antenna. All right, so this is the antenna that is used for communicating lots of data back and forth between the Earth, okay, and the probe. And remember how in the Earth they have three different locations where they have also antennas that receive the information here from the probe. So the reason why you have three is so at any time of the day or night, there is always one of these antennas of terrestrial stations being able to see the probe and receive the information. Okay? Yeah. Mm-hmm. Yeah, so let's see. Then we have these, the LGA are the low gain antennas. So these are more for sending instructions that are briefer. So if you don't need to send a lot of data, you can use the low gain antennas. Then you see here that there's the ion propulsion thrusters, the ion propulsion system thrusters, and there's three of those. One here, one underneath, and one over the other side. All right? And so depending on which one they use, you can maneuver the probe in order to change the attitude. Okay? There's also the different, the smaller engines. Remember the RCS thrusters. Okay, these are, let's see, the RCS. Reaction control system thrusters. Those are the hydrazine thrusters that change the position of the probe. They fire just for a few seconds each time, and it's just to do small changes, okay, faster changes than with the ion propulsion system. It also has gyroscope. Okay, a gyroscope is essential to know where the probe is. It has a star tracker, and it's basically a way to see where the stars are and being able to understand and position where the probe itself is. Okay. Then we have the coarse sun sensor. Is also another way, the CSS here, the CSS, coarse sun sensor, is a way of knowing where the sun is. And so there's a few of those, okay, on the top and the bottom, in order to also, in each corner of the probe, you have one of these sensors in order to see where the sun is. If the probe can find the angles to the sun, then it can also determine where it is. Okay, does that make sense? So we have seen so far the communication systems with the antennas, the propulsion system with the ion thrusters and the hydrazine thrusters. Okay. Then we were looking at the location system with the coarse sun sensor and the star tracker. All right. And then the experimental components here, you have a framing camera that is basically a camera to take pictures of high velocity and high fidelity. Okay, so this is a really good camera. That is what they use to do the mapping and everything. Mm-hmm. Oh, I'm so sorry, Christopher, that this keeps on freezing. I feel so bad about that. There's nothing I can do, at least at this point. I hate it. The gamma ray and neutron detector, the GRAND, okay, is right here, is this part. Okay. Terrible connection. Oh, I feel so bad, guys. So this apparatus, this instrument is designed to be able to send either light signals or radio signals to the planet, to the asteroid, and then as it reflects back this light, they are able to do an spectrometer analysis to find what are the minerals on that area, on the surface. Okay. They also have the visual and infrared mapping spectrometer. Okay. So that is the other instrument that they use in order to also visually, with light and with infrared light, they are able to map the surface and the subsurface of the asteroid. An spectrometer basically works this way. Let me see if I can explain this. Okay, so have you ever wondered or asked yourself the question, why do things have the color that they do? Okay, why is my skin, kind of skin color? Okay, why is my ring?
Why things have
this like color? Rodney?
It's kind of the light it hits on that helps define colors.
Okay.
We also have internal color as well.
Mm-hmm. So when light hits something, that object, depending on what is the molecular composition of that object, is going to bounce off light, different spectra of light. Okay? So the different material reflects different wavelengths of light. Okay? And so, for example, gold, when it's hit by light, it reflects a lot. That is why it's shiny. And it reflects that the gold color precisely. Okay, so my skin has a different material, so it reflects a different color. My hair has proteins and everything that reflect kind of the brown, dark brown color. So Christopher, you are absolutely right. It reflects some light, the light of that color, and absorbs the rest. Okay. So the same thing happens when the probe, when done, shines light or infrared light on the comet, on the asteroid. Sorry, it reflects a certain type of light. And so these spectrometers, these instruments, what they do is they capture the reflection of that light, and they are able to analyze specifically what are the elements that that light is reflecting, because each element has a different spectral signature. Okay, it reflects a specific type of light. Okay. So Sabrina says a tomato will absorb all but the red light. That's right. Okay. All right. So, no. When you are eating food, you are actually eating the material. You are not eating the light. The light is what is reflected. Haley, come on. Come on. All right. So that is why things have different colors. And so what they do, what scientists do, is that they are able to reflect light, okay, and by seeing what comes back, they are able to analyze that and see what was the light that was absorbed and what is the light that is emitted, and that is going to actually show you the particular components of something, okay? When we are going to study in the next weeks, when we are going to study rocks, igneous rocks, and everything, we are going to come back to this issue of spectrometer, spectral analysis, because that is the same way how geologists here on the Earth are able to find what is the material, what are the elements in a rock. Okay. Yeah, photons have a very, very small mass. Technically, you don't have any mass. So yeah, you are eating actually not the light. Okay, is the material. All right. What is a photon? So physics. I think that next year we are going to do physics and chemistry. Okay. Yeah. So. No, solids are solid. Okay, let's go in a little kind of tangent here. The reason why when I touch something, okay, I feel that as a solid or a liquid or something is because actually of the electromagnetic resistance between the molecules of one body against the molecules of the other body. Okay. Did you catch that? Because if you actually think about it at the molecular or atomic level, there is a lot of empty space between electrons and protons and neutrons. Well, the neutrons and the protons are really, really tight, packed together in the nucleus of the atom, but there's really a lot of empty space between the other ones. Okay, so let's see if I can repeat that again. Okay, so what I feel when I touch something solid is actually the electromagnetic resistance of the molecules of one body against the molecules of the other. That is why they are solid and they don't go through. Even though there's a lot of empty space between the molecules and in the atoms themselves and everything, the electromagnetic forces repel the molecules, repel each other, and that is why I cannot penetrate the solid surface. All right? When something is liquid, my finger can go right through a liquid because the electromagnetic resistance of the liquid is less than the other solid body, and so it actually, the molecules move out. They are not tied together like in a solid, and that is why it's a liquid. Okay, so now you get it. Okay, great. This is not necessarily quantum physics, Christopher. Okay, but it is really it is really physics. Okay, it's more on the classical type of physics. Okay, I'm so sorry that the connection is bad, and yes, if you want, please, okay. Watch the video later. So Mackenzie says that actually makes sense. Gosh, I think I get science. Ah, great, excellent, good deal. Okay, so did you see how when we were talking about the ion thrusters, the ions, you know, that are accelerated and pushed out, okay, remember that one of the laws of Newton is that for every action there's an opposite and equal reaction. Okay, and so as the ions are pushed this way, they cause a little thrust the other direction for the probe. Okay, so and again, it's just as gentle as a piece of paper on your hand. So not a very strong thrust, but that is enough to move the probe forward. Okay, so, and the same thing when you push against two things together, you are actually thrusting. Okay, and you can see the action and reaction between one and the other. Okay, so very good questions, very, very interesting. So okay, so Sabrina says solids, strong bonds. Very, very good. Very strong molecular bonds that don't fall apart, and that is why another object that cannot penetrate. In liquid, you have medium bonds. So the bonds are not, they are not between the molecules. The liquid, basically, the molecules can move freely between one and the other. In a gas, the molecules are not bonded at all. They move freely, and there's other molecules in between. So in a gas, there's really no resistance, okay, you know, to that. All right, excellent. Okay, so now we have photon here on class. Woo, excellent, good deal. Okay, so all this was basically to explain to you how Dawn can look and analyze the surface and the internal composition of these asteroids without actually landing there. Okay, so one of the, you know, remember in the assignment, one of the purposes of the mission, they said, was to bring back lunar samples in order to analyze what type of minerals they have. Okay, could you analyze the composition of the moon without sending a probe to the moon? Could you analyze the composition of the moon without actually sending anything there? I can hitch a ride with Virgin Galactic. Oh, they are not yet going there. That will take quite some time. Okay. Can you analyze the composition of the moon without actually going there? Yes, lots of money certainly can fix that, and they are actually trying to fix that with lots of money. So, so take your seat. Mhm. Emma says, I want to say no, but I have a feeling I'm wrong. So remember, what were we talking just now about spectral analysis? Can we get light from the moon? Can we see light coming from the moon? Shining on the moon and coming back? Any takes? Okay. You can tell when it's what's on something based on analysis of the reflected light. That's right. Oh, okay. So the question is, can you analyze what is on the surface of the moon, what minerals are the composition of the moon without going there to the moon? You can, that's right, yes. Sabrina says you can. Absolutely. So that is actually how, scientists have been able to know what is the composition of the moon, what is the composition of Jupiter, of Mars, of, everything, all the different planets is because of the light they reflect. Oh, wow, I get cut again, always at the same spot. What is the composition? What is the composition of a planet or a celestial body without going there? Okay. So yes, the answer is yes, you can analyze the composition of things just by looking at what light they reflect. All right. So for example, Mars has a red colored, a reddish tint to the planet Mars. Why? Why does Mars have a reddish tint? Okay, while you work on that, let's see, here we have in the website, this is all in the JPL website, the Jet Propulsion Laboratory. So Sabrina says iron oxide causes that reddish orange hue. Exactly, that's right. Can you see? So even with the naked eye, we can tell that Mars has a lot of iron. Okay, of iron oxide because of the light that it reflects back. And so by doing this spectral analysis, we can actually see the composition of the planets. We know that Jupiter is made of gas and everything. Oh, the irony. That is great. Very, very good. Okay, so here in this page we have what are the mission objectives of the Dawn project. Okay, so the top level question that the mission addresses is the role of size and water in determining the evolution of planets. Okay, so Ceres has water, Vesta does not, and so and they are kind of in a similar neighborhood, and so it is important to try to see how are they composed, and is Vesta too small in order to keep water in its gravitational pull, and that is why it doesn't have water? Do you need a size at least like Ceres in order to keep water? These are kind of some of the questions that Dawn is trying to answer. Okay. This one is a really cool graph showing the trajectory of Dawn. So it is launched, okay. Then it went beyond the orbit of Mars, and then it went in February of 2009, it went right by Mars, right below the orbit of Mars, to do what is called a gravitational assist. Okay, what is a gravitational assist and how does that work? Okay, how does the gravitational assist work? Any ideas on that? Do you remember when we were studying Kepler and that one of the laws of Kepler was that when you have a body, that the bodies go orbit in elliptical orbits, and so when something goes closer to the gravitational body, it accelerates. Okay, it goes faster, and then it goes slower as it goes out. All right. So Emma, let's see what do we have here. It says use the planet's gravity to pull you along and slingshot you around. It saves fuel. That is absolutely right. It saves fuel because it accelerates the probe a lot, really. Okay? So it's when gravity assists and gravity tends to pull it in. It is tend to pull it in, but as it goes around, remember that, if you enter into an orbit, when you get closer, you accelerate, okay? And then at that point, if you put your thrusters on, you can escape the gravitational pull of the planet, but you will go a lot faster. Okay. So Rodney is still on the other one. So does the light tell us the full composition of the planet? I don't know if it tells us the full composition of the planet. That is a good question. I think that it tells us the composition of the surface because you can actually see what is the light that bounces off there. Then scientists use other techniques in order to find what is inside the planet. Okay, one of the ways is by measuring the mass of the planet and then the volume, and then you can calculate the density of the planet. And by the density you can see, well, in order for something this big to weigh this much, it has to have this sort of elements within. And so they theorize that way in order to find that out. Okay. If you actually want to see the composition inside the planet, you would actually need to send something in there in order to send sound waves through. Okay. And so the same way that light bounces off and reflects differently, when you send sound waves, it also reflects differently depending on the composition of the layers of the planet. And that is what geologists use here on Earth to determine what is underneath the ground. Okay? Does that make sense? I hope it does. Okay, I hope they didn't cut too bad. Okay, great. All right, so don't receive a gravitational assist from Mars. Then it departed the orbit of Mars and it went there to Vesta, and we saw how it went into orbit around Vesta, and then slowly it left the orbit of Vesta and now is actually here by Ceres and entering into orbit of Ceres. So it actually entered the orbit of Ceres not too long ago. So this is the current position. So the color of the planet detects what is on the surface, but not deeper down. That is my understanding, Madeline, that you can actually, by this spectral analysis, you can see the surface, but not totally what is within. Okay. The infrared light penetrates more, and so you can actually, I believe that they use the infrared instruments in order to go through things and then receive information on what is in the underneath the surface. Okay, but I really would need to confirm that. Okay. Let's see, mission status. Here we have that. We have different images of Ceres, and this is interesting. These are images kind of being received in reverse order. So these are the images of Ceres as dawn was getting closer, and you see how they are getting better images the closer they get. Okay, so this is the first page, so it's really a good set of images there. There's something actually really interesting on Ceres, which is in one crater there's a couple of lights there. Okay, and I have no idea what they are, and I think that no one knows really what they light. So like the planet, light only bounces off of the outside of the orange. You can only see the segments when you peel it or cut it out open. That's right. That is good. Good explanation, Sabrina. Very good. Okay. Let me see. Oh, this is an interesting. Okay, this is a very interesting video showing how dawn enter into the orbit of Ceres. Okay, Ceres is considered a dwarf planet because it is much larger than other asteroids. So the definitions are kind of iffy in this sense. Okay, between asteroids, planet, dwarf planets, protoplanets, and whatnot. One of the considerations is the shape. Okay. If this body is pretty much like a sphere, okay, if it's very spherical, then it is considered more to be a planet or a dwarf planet. If it has cleared out its neighborhood of other asteroids or meteoroids and so on, okay, then it is a planet. That is the difference between Vesta, Ceres, and let's say Mars. Mars has cleared, the neighborhood of other planets. Ceres and Vesta have not. Okay, so let's look at this video and see how Ceres enter into orbit. All right, let's see. So this is January 9th. So this is day by day. Okay. A day-by-day approach, and here you can see Ceres being approached, and the probe as it moves around. The line is just to show us the trajectory. So it's coming from Vesta, going past Ceres, and then it puts the thrusters in front in order to slow down and go back. And see now how the ion thrusters are going in the other position to also slow it down in the other position and start going into orbit. Once it's in orbit, you don't need the ion thrusters anymore. Okay. So Ariel, thank you for joining us. It's okay. You can catch the rest of the class in the video later. All right. So see the shape here of the orbit of Ceres, of dawn, around Ceres and how it entered into orbit. So the entering into orbit is what happened just now in March 6th. So see there, May 6th. Oh, sorry, May 6th of 2015 is when it's going to be in this orbit. Let's see where it is now. At this point, so we are March. Okay, let's see. Okay, March 6th. Okay, there we go. March 9th. So today is the 10th. All right. So it has already gone by the closest here approach so far. All right. And now it's here on this trying to slow down in order to go back and go. Oh yeah, today is the 11th. Thank you. So let's see. A little bit more. There we go. Okay, so that's where we we are right now, just to be precise here. Okay. So, but see, it takes a few days to slow down. Again, remember that the push is very, very gentle, and so it takes some time to do this orbit. Okay. When do you think we'll get some pictures of the surface of Ceres? So actually, we have already been getting lots of pictures. Now is they said Ceres is in the dark side, so the probe is in the dark side of Ceres. Okay, you can see it here in this animation. If it's around here, we are kind of on the dark side of Ceres. But when it went through this area, it actually took a lot of good pictures. Let me see if I have some of those open here. Okay, let's see. So, so you can explore. Okay, so these are some of the pictures of Ceres that have already been sent. So this is the one, and that scientists don't know what is causing these lights. And it's interesting because in the video, the full animation, the lights are actually moving with the planet. Okay, so I have no idea what these are, and I'm dying to know. So, is it aliens? Well, it would be Serenians. Okay. It is actually kind of mysterious because, some people say, well, it's the reflection of something. Okay. Well, the sun is over here. So if something is reflecting and reflecting at 90-degree angles here, I don't know what that would be. Okay, and also it's reflecting very, very bright. Okay, so is it metal? Okay, could be. What kind of metal would have the spectral reflectivity of this? That is kind of the question. Can you see that how now that we know that light reflects out of different elements differently, that is the question that we have to ask ourselves. Okay, what is reflecting that? And the main also problem with that, okay, you have the craziest names, is that these lights were actually, like I was saying, they were moving as the asteroid was rotating. The lights were moving inside that crater. Okay, so they were at the same spot. Okay, so it was moving with the asteroid. So the mystery is still on. I don't know what these lights are, and we do have images, okay, but we need to find more out about what they are. Okay, very, very interesting thing. So what I'm going to ask you to do, okay, so today, because we did this kind of special lesson, well, scientists have already been to the moon. Okay, so the question was not can we go to the moon again, but the question was why do we want to go to the moon again? All right. So the interesting question here now is that they went to Ceres and to Vesta in order to find new things. Okay. And who would have known, all right, the things that they have already found. So it's very, very interesting. All right, so now the assignment that I'm going to give you is going to be, again, as a team assignment, okay? You can review the assignment that you did for lesson 17. And now, remember that in lesson 17, you were basically just to define what was the mission that you wanted to do. Some did a little bit more than that. What I would like you to do is to, given that mission, what type of probe you want to send. Okay, some of you want to send a very large probe, a lunar rover or whatever. If you want to stick with that, that is fine. But I want you to basically calculate, okay, estimate from what you know, what type of rocket you would need in order to launch that into space, okay, and what trajectory you would have. This is going to be due in 2 weeks, okay? So I haven't put the assignment on, but I'm going to put it on in this lesson 24. This will be kind of actually I'm going to make an extra assignment, and then I'll send you the announcement for that, okay? So, but this would be basically a complement to this to the space project, all right? And I want you to do it together as a team again, okay? I think that is valuable. There are still a couple of teams that haven't turned in the previous assignment, okay? So let's go ahead and finish that up and then do this one. All right? Okay, well, I hope that this has been interesting to everyone. It has been very interesting to me, okay? So I have really enjoyed the conversation and the questions, okay, and the collaboration. Okay, who would like to offer a prayer to finish the class? Abigail, do you have a mic? Would you like to pray? Okay. Anyone? Anyone that has a mic? Okay, excellent. Thank you.
Our dear kind Heavenly Father, we're thankful for this day. Thankful for all many things asked from us. Please help us with our assignments, that we may stay on top of them, that we may get them done. Thankful for Pablo. And his taking the time to teach what are going on. Please bless him. These things we pray for in the name of thy Son, Jesus Christ. Amen.
Amen. Thank you very, very much, Rodney, for that. Okay. All right, let me finish here the video.